speakers on the sofa. Very good. Now you grab one of the microphones here, whichever you like. How good?
Can you hear me? Oh, yeah, it's good.
Okay, so our next speaker is Yifan Mao, who will talk about constellation, efficient and resilient peer-to-peer overlays for federated Byzantine agreement systems.
Thank you for the introduction. Hi, I'm Yifan Mao. Today I will talk about our constellation. It's advised by my advisor Shailesh and cooperate with Marta and Giuliano. Peer-to-peer network plays a fundamental role in the operation of blockchain technology. These networks facilitate the decentralized nature of blockchains, as they allow participants to communicate directly without central authority. P2P networks are instrumental in distributing the data across all the nodes in the blockchain network. They are responsible for enabling the validating of transactions and blocks. Despite the crucial roles, P2P network also introduce a lot of challenges that affect the blockchain performance. One primary constraint is scalability. As more nodes coming to join the network, the consensus process can slow down due to the cost of bandwidth and reduce the blockchain's transaction throughput. The latency and the data propagation delay can also be hurt. Another crucial concern is the security. Take the Eclipse attack as an example. Attackers may isolate a node from the rest of the network, potentially leading to the double spending attack or some other vulnerabilities. In the blockchain P2P design, the use of random graph is the common practice to establish the network topology, where each node has a random set of the connections to prevent the centralization. The flooding gossip is another widely adopted practice in blockchain P2P design. Both of them are easy to implement and are believed to be secure. While this approach ensures data propagation, it can be data resource intensive, causing increased bandwidth usage. To mitigate this challenge, fast relay network applies a lot of techniques here. For example, the compact block relay and the transaction relay. By sending only the essential data, fast relay network significantly reduce the resources required for the transmitting information across the blockchain network. In our work, we assume the flooding gossip protocol among the nodes in the network, and later we will take the random graph as the baseline in the evaluation. Federated Byzantine agreement is the alternative consensus mechanism that differs significantly from the proof of work and the proof of stake. Unlike proof of work, which relies on the miner expanding computational power to secure the network, or the POS, which just involves the token ownership for the consensus. FBA operates a principle where the nodes trust the currents for the consensus. Such decentralized control has affiliate assumptions that allows partial of its trusted currents to be fair and still achieve the consensus. FBA network also require robust and efficient communication among the validators. Latency, bandwidth, and security based on the column sets are all crucial aspects of the network design. As the federation grows, the challenge of maintaining the decentralized characteristic becomes more important. Then what is FBA? Here is a small example. So suppose that we have the V1 to Vn, that is a set of the validators in the network. We call them as the column slice to the validators who trust them. And we have the trust assumption that there are at least one slice to be honest and available at any time. Sometimes it can be much larger. And then just how to consensus the node trust. So for here that assume that currently if V3 is the node validator that to be active and honest, then the colon slice example for 1, 2 that both contains V3 can be a valid colon slice. We will talk about them more detail later. In practice, Stella's network currently comprises several top-tier organizations as the figures plot on the right. Each organization has around 3 to 5 validators and run these validators. Among the organizations, there's a threshold named as the colon set to reach the agreement. So for the example here, that the threshold is 2 for all the organization with size of 3 and threshold of 3 for the organization of 5. Smaller organizations trust the larger organizations, which lead to their tiering hierarchy. To achieve the 7 top-tier organizations as an example, the smaller organizations require the 5 out of 7 organizations for the agreement. And for each agreement with one organization, they need more than half of the validators inside this organization to agree. So for example, like we first need the 5 out of 7 among the organization, and for the 5 organization, we still need to have the threshold. We have some measurements of the P2P network state in Stella, and the results show that the network is not effective. So in a 23-node network, we increase the node fan out with time going by and focus on the duplication. The top figure shows that there are more duplicated bytes per second when we have more node fan out. So so that there are node fan out of 10, 16, 23, and we run each of them independently. Network performance is not optimal. Significant message duplication occurs during the surge pricing and non-optimal overlay diameter. So to improve the network efficiency, but without affecting the fault tolerance guarantee, how should we optimize the network? Before we talk about the solution, let's first summarize the network design problem here. So with the measurements from the last page, we want to design a decentralized P2P topology construction that is bandwidth efficient. To ensure low propagation latency across the network, the second requirement is that the new design needs to minimize the network diameter. Also, that the FBA trust assumption must be satisfied. Note here that the P2P design at Stella is a bit different from the P2P design in the POW or POS, as they do not utilize the underlying trust assumption of the blockchain. So in the next half of the presentation, we will show the network design. Currently, we focus on the top tier nodes and with the assumption that we are applying the flowed gossip protocol. For the FBA trust assumption mentioned before, here's a small example. So for a validator N, it wants to have the connection to the organization A, which has 3 validation and a threshold of 2. So as we talked before, that the threshold of 2 means that there must be at least 2 validators to be active and honest at any time, but it's unsure. So that there are 4 cases on the right. So due to the uncertainty of the the active and honest validators, so yeah, absolutely, N can have the complete connection to all the 3 validators. In this case, it can always have the connection to the honest and active validator. Otherwise, if it only connects to the A1, but at that time that is only A2 and A3 are the honest nodes, then the trust assumption cannot be achieved. And today we will present the consideration. It's a decentralized topology design protocol. Our protocol can guarantee that each validator is connected to at least 1 validator within a available colon slice to achieve the consensus agreement. And it can also achieve a near minimum network diameter and a node for fan out. Our experiments show that the consideration has 50% higher transaction throughput. In consideration, we have two main designs to minimize the fan out. Locally, we solve the validator's connection as a set cover problem on intersection to each of its colon sets. Globally, we build a cluster-based network structure and ensure the significant overlap between the validators' connections to minimize the fan out without affecting the diameter. So on the local part, we will continue this, the example before. So that when the node N, it wants to have the connection to the org A with a threshold of 2. So previously we say that we show that the complete connection is totally fine, but it can be wasteful so that we connect to all of them. So can we just have a lower connections? Yet is so that, for example, in this case, that the threshold of 2, so that as long as N can have has two connections, it's sufficient. Since that the threshold is 2, so that the two connections must have at least one honest and active validators to connect. And based on such idea, we can just drive this fan-out minimization from the connection to the validators to the connection to the organizations also. So for example, for the colon size for N, that it has a colon size for the 3 organizations, A, B, and C. And for here, let's assume that the org threshold is 2, so that there must be at least 2 organizations to be active and honest. But actually only the N only needs to connect 1. So that as the validator N only needs to connect 2 orgs, and inside the 2 orgs, it can use the similar thing that to connect 2 validator or 3 validator. So in this way that based on the colon size, N can find the minimum number or just don't need to connect to all the validator, but it's partial of them, and to achieve that to connect at least one honest and honest validator. Second, we consider the problem in a global side. So that in the global side, we have a small example here. So that suppose we have 5 validators here, and we require each validator wants to connect to at least 2 other validators. So for here on the left side, there's a random topology. So the random topology is totally fine. That yeah, everyone is happy. They have 2 connections to others. But what if that we build the connections that is, if they can sharing some information so that they can have the sharing connection so that we can optimize the topology with the degree of 2. So that on the right side that they still have connection to the 2 other validators, but with less degree. And based on the 2 designs, we combine them together. And here's the example of our just combination of the 2 design of the fan-out minimization. So let's still have it as an example. So we first have the example with 9 organizations with the uniform and running 3 validators. So based on the Stellar's design, so that the 9 organizations, that the threshold is the floor of 2/3 of N plus 1, so it's 7, which means that if we connect to 3 organizations, then we guarantee to have the intersection with any set of the threshold of 7. And so we group the organizations into 3 clusters. So we have the 3 cluster A, B, and C, and each cluster has 3 organizations. And for each organization, they first have the connection, they have the age to all the other organizations in the same cluster. And then they have at least 1 age to the other cluster. So that, for example, for the A1, it has the age to the A2, A3, as they are in the same cluster. And it also has the age to the B1 and the C2, so that it has the connection to the cluster B and the C. And for here that we do, we just build the topology for all the nodes so that they all of them have the in-cluster connection and the out-cluster connection. And for here, the age for here is the complete bipartite graph, so that which means on the left side, all the validators have the connection to all the validators on the right side, so that which means that they have complete connection on both sides. In this way, actually, we can achieve our requirements, so that actually for here the diameter is small, so that diameter is at most to be 2, and for here that the consensus agreement can also be satisfied. But for here, can we do it much better? Can we do it better? Since previously we mentioned that for all the organizations, there's an inner threshold, and the inner threshold is around 1/2, so that but actually the previous one didn't make use of it. So for here that we design another org-to-org connection, so that on the left side, on the right side, it's a complete connection, so that validator to all the validator. But on the left side, that validator only connect to the minimum number. The minimum number is what we just talked from the local design, so that it's based on the target organization size and the threshold. So in this example, that they only connect to 2. Then by introducing the new connection type, so that later just to simplify our description. So for here we just say that we have the complete connection as a solid edge, and the dotted edge to be the connection to connect minimum validators. So for here, we find that we can build the network that for all the inner cluster edge, we can replace the solid connection to the dotted connection. And by changing these connections, we can decrease we can minimize the degree, minimize the fan out, and we can still keep the diameter of 2, so that it's an optimized version compared with the previous one. So for here, that why the diameter is due 2. So for here is the example. So for here that note that so for here that we have 3 different parts. So that let's start from B1. So that for the other orgs with B1, that B1 has 3 parts to the other orgs. First is B2, B3, so that they have the dotted cycle connection. And for the A1 and the C3, they have the direct solid connection. And for the A2, A3, C1, C2, they have the dotted connection plus a solid connection. So in this figure, in this page, we plot all the 3 parts with a cycle of dotted, with the solid distance and the solid plus dotted. So for here, we start with the red one. The red one is any validator in the B1, so that it starts from 0 and then go one hop to B1 and go the second hop to B2, so that we can find that for all the organizations in whatever parts that the hops is no more than 2, so that it can make the network diameter to be 2. Then so the example we showed before, it's just for the n equals 9, and we assume that all the organizations have 3. But actually, we can just derive the example to a more general case, that we have n organization, and each organization I runs the number of n sub I validators. And the column slide here is that it's still the flow of 2/3 of n plus 1 organization. And inside each organization I, the flow is half of n plus 1. So that it can work for like 10, 11, 12 organization, and the size can also work with 5 or 7. And similarly, since that the threshold for the organization is the flow of the 2/3 of n, so that we can still cluster the organization into 3 clusters, and with the similar setting that they have the dotted connection to all the cluster in the to all the organization in the same cluster, and have at least 1 solid connection to each other cluster. And here, and we implement this design to the Stella testbed, and for here it has some evaluation results. For here we plot 4 curves here. So the blue curve is a complete one, so that the 23 nodes have the complete connection, so that it has a maximum fault tolerance, but also has the just the worst transaction rate. And then for the orange one, it's the random degree with 16. It's a representative of the current configuration. And the above, the top one is the green one is the random degree of 6. Yeah, it looks good, but it cannot guarantee the fault tolerance. So we implement our consideration that it's optimal. So first, it can achieve the optimal fault tolerance, and also that it can has 50% higher throughput than the curve of the orange curve with the degree of 16. And all our previous work are based on the top tier nodes. And our next step is the network design for the lower tier nodes. So first, let's define the lower tier nodes so that they are the nodes that trust the top tier nodes, but almost nobody trusts them. So they're like the small organizations and others. And the problem is that previously we built the network design based on the trust assumption, so that we can use the threshold and we can do a lot of things. But for here, that is an absence of the trust assumption and about the low tier nodes. And so our current plan is that we want to establish the connection based on the utility of the transactions received from the nodes. And the utility here is we defined based on the number of transactions received from a node that can end up successfully to executing on the ledger. And after that, we hope to have the network design at the top tier and at the lower tier, and also between the top tier and the lower tier. And for here, okay, so today we've talked about the constellation, and we've showed our design that how to make it to connect to all the column slides to achieve the consensus, and also how it makes the diameter to be lower than 2 and with the minimum node fan out. And our results show that it's 50% higher throughput compared with the testbed evaluation. Okay, that's all. Thank you.
Any questions? Yes.
Is how much of this topology construction can validators do individually versus how much is like a global computation?
No, it's a local computation. So that we have a decentralized algorithm so that for the nodes to how to find the cluster, join the cluster, and leave the cluster, so that they can have the communication to the others and find the ideal cluster to join.
Any other question? Nothing on Zoom. Okay, great. Let's thank the speaker again.